So in this meeting, I'd like to focus on these two topics. The first one is evaporation-induced mesoscopic order from the isotropic Georgia solution. The second one is morphological evolution of mesoporous inorganic silica. The third one is hexagonal to cubic phase transition in nanostructured polymeric resin, polymeric material prepared by water-induced reverse micellar templating. As you know, the porous material can be classified like these three types: the microporous material, mesoporous material, and macroporous material. Basically, the mesoporous material has many potential applications in the sensor and the photonics and the electronics and some bioprocessing and catalyst. So I'm going to focus on this mesoporous material, the morphological control based on source and processing in this meeting. So mesoporous material. Most of mesoporous material have been synthesized by these two methods. The first one is hydrothermal precipitation method in aqueous media. The second one is the Georgia processing method. And as I said, in the rest of my talk, I'm going to focus on the dissolvent processing for the making of mesoporous material. I'm going to talk a little bit about these two methods. In the hydrothermal, the precipitation method, the ionic and non-ionic surfactants are dissolving the aqueous media, H2 and ethanol sometimes, with an acetyl base as a catalyst. And the solution of the organic phase is blue CMC. And this organic phase solution is mixed with the inorganic source solution with normally the TIOS and LUDOS and the other inorganic source. And they form the organic and inorganic self-assembly with the lyotropic liquid crystal-like order. And then this self-assembly is then heat treated to be polycondensated to form the inorganic continuous interconnected framework. Actually, the final product is always in the form of the powder from this method. On the other hand, in the Georgia processing method, it is pretty much simple. We put everything together in this bath and then let them evaporate to get the interconnected network of the inorganic material. And the shape control and morphology control of this material is easier than the hydrothermal precipitation method, and we can create the monorace or synchrone or any kind of bulk material using this Georgia process method. And many equipment can be used for characterizing the nanostructure of these types of material. But the neutron is very useful to have enough scattering from the nanoscopic order in the aqueous solution or polar solvent. The bottom here shows the sense configuration of sense setup in Cary, in Daejeon, Korea, and we use the neutron wavelength is equal to 5.08 angstrom. And to have a contrast matching between the silica and the solvent media, we add a certain amount of D2 in the solvent media to have micelle to be only scattered by a neutron. So I'm going to move to the first one, the evaporation-induced mesoscopic order from the isotropic Georgia solutions. In order to prepare the Georgia solution, we make approximately 38% the organic phase solution with the trivalent polymer, PO, PPO, PO, the commercially named as P1 to 3, and the numbers are mole fraction of each unit in a single polymer chain. And this organic phase is mixed with this inorganic phase solution with the keros. And they mix them together and reflux and stir and age it for several minutes, 50 minutes, 50 degrees C, and to get the interconnected organic and inorganic sub-assembly. So we would like to see what kind of pathway and what kind of synthetic mechanism to reach this final product. So we would like to see that kind of procedure using the sense. The left figure shows the sense data of the P123 and P-Joseon solution during evaporating the solvent by sense. As you can see, it is not so clear in this picture, but the very sharp, the polymer, the P123 micelle, the very sharp peak from this polymer micelle is abruptly disappeared just after mixing with the inorganic solution. Then the intensity comes back to some certain range during evaporation, and in the final stage of evaporation, it moves to the wide angle region a little bit, and the intensity slowly comes up. And based on this data, we can propose this kind of schematic model for self-assembling procedure. As you can see, that we have a very nice micelle in organic solution, and then just after mixing with the inorganic solution, this micellar order is disappeared, and we have some isotopic state, organic and inorganic mixture. Then during evaporation, the micellar, the association between the organic phase is actually the hydrophilic part of the polymer and the inorganic phase that associate then to form the organic and inorganic self-assembly during evaporation. Then after completing the packing of the micellar structure, then the polycondensation takes place, and then we have a very nice organic inorganic interconnected self-assembly. Based on this schematic model, we can just propose the formation mechanism for this kind of material synthesis. As you can see, that we have a very nicely ordered micellar solution for the first in the initial in the organic phase solution. Then just after mixing with the inorganic solution, we have an isotopic phase. Then after stirring for several minutes, and we have the odor comes up, and then during evaporation, this organic phase and inorganic phase start to associate each other and to make a self-assembly up to a certain point of evaporation. Then after the completion of the organic and inorganic micellar structure, and then the polycondensation or the framer phase take place, and then we have finally the organic and inorganic self-assembly. But as you can see, that the peak is moving to the wide angle region is due to the polycondensation of the inorganic material, and then it decrease the intermicellar distance a little bit. Therefore, the peak is goes to the wide angle region, and the small shift to the small angle region of the during evaporation is due to the association, the growing association of the organic and inorganic compound during evaporation. So the second part is, next one is morphology evolution of the nanosphorous inorganic silica in Joseon processing method. And first of all, I would like to remind you of the classical, the morphological spectrum of black polymer. As you can see, changing the volume fraction of each black segment, we can change the morphology of the black polymer from spherical, sphere, and cylinder, and double gyroid, and blah blah blah. As you know, we have this kind of morphology spectrum, and with the same concept, we can control the morphology of the organic and inorganic self-assembly. We have organic phase, organic material like cationic surfactant and anionic surfactant, and non-ionic surfactant too. And this, when we change the mixing ratio between the organic phase and inorganic phase, we can change the morphology of the self-assembled structure, because the inorganic material is associated with the hydrophilic part. Hydrophilic part of the surfactant, and then if we change the amount of the inorganic addition, we can change the volume ratio between the hydrophilic and hydrophobic and hydrophilic part, and we can change the packing ratio between two. Then we can change the morphology of this self-assembled nanostructure by using the different mixing ratio. So we prepare this the Georgia solution using the TIOS and the P1 to 3 tribal polymer, and we make a tribal polymer approximately 38% and mix it with the TIOS inorganic solution and the Liplux, then stirred and age it for several 15 minutes or a little bit more. And in the Georgia, during making this Georgia solution, the TIOS and actually polymer, but if we change the polymer mass, polymer weight, we can change the TIOS and the EU, the molar ratios. In the Georgia solution, TIOS EU molar ratios varies from the 20, 40, 60, 100, 140. So when you change this TIOS and EU unit mass ratio, we can change the morphology of the self-assembly structure. So this is the final shape of the organic and inorganic self-assembly self-assemblies. And as you can see, TIOS and the EU unit, ethylene oxide unit, the ratio, molar ratio is 20. We have like a monoid structure, and we have sometimes thin film, and sometimes we have bulk. And we take these samples in the SAX measurement at PAS in Pohang. And as you can see, we have a two-dimensional X-ray patterns for the TIOS and EU unit. Molar ratio is equal to 40. And when you take a look at these two-dimensional X-ray patterns, we can see some green here, and the other one here, and it is not so clear, but we have another one very close to this sharp green. And based on this two-dimensional X-ray pattern, we can plot the one-dimensional X-ray scan data, and as you can see, the 100 and 110 and 200 X-ray pattern. We clearly see these kind of reflection patterns, which can be indexed by the two-dimensional hexagonal columnar lattice. So the material, the organic inorganic self-assembly with the TIOS EU, the molar ratio is equal to 40. We have a hexagonal columnar structure. So this data shows the TM micrographs of the calcite samples with the various TIOS and EU molar ratios. So at the TIOS and EU molar ratios is equal to 20, we have this kind of like a platelet-like structure. And when we increase the TIOS, the relative weight of TIOS in the Georgia solution, we have this kind of nice hexagonal pack structure, and the other one is like a worm-like micrograph. And when we increase a little bit more, 80 and 100 and 140, we have like a platelet-like structure, indicating the absence of the mesoscopic order in the structure. And we take this material in the BET analysis, and this data shows the nitrogen, the absorption and desorption isosome. And the left figure shows the BT data for the material with the tails and the EO unit is equal to 20. As you can see, the data is like data shows the typical isosome for the slab-like material, indicating the absence of mesoscopic order in the structure. Probably this kind of the destruction of the mesoscopic order is due to the spherical morphology, which can be readily destroyed during calcination. And when we increase the chaos in the Zozon solution, we have a very nice surface area to have this kind of isosome, indicating that we have this kind of open channel columnar structure. And when we increase a little bit more, we have a little bit more hysteresis increased, indicating that this channel is distorted, and probably this now is moving to the sort of the gyrotic structure. So when we change the chaos and the EO molar issues, we can change the morphology of the mesostructure of the mesopore silicon material. So we're going to move to the third one, the hexagonal cubic phase transition in nanostructured polymeric material prepared by water-induced reverse micellar templating. Okay. We thought about the reverse situation that we put the micelle in not in the aqueous media, in the organic solid media. Then this micellar structure is changed into this way. So hydrophobic part is located in the corner part of the micelle, and the hydrophilic part is in the core part of the micelle. So we make a reverse micellar structure in the organic solvent with D2, and changing D2, we can change the morphology of this polymeric nanoporous material. So this data shows two-dimensional science data of the reverse micellar structure. Actually, this is the solution state, and the polymer state is almost same as this one. As you can see, when we change the W is equal. W means that the water and the polymer, actually the ethanol oxide unit molar ratios. So when you increase the amount of water, we can change the two-dimensional sense data. So based on this two-dimensional sense data, we can plot the one-dimensional sense scan data too. When you look at this data, when you increase the water content in the Georgia solution up to W is equal to 1.3, we have almost same peak profile. Then at W is equal to 1.55, we have some change in peak profile. We have some peak in the left shoulder of this peak, major peak, and there is some other peak comes up. And the W is greater than the 1.55. We the peak profile is almost same. But when you take a look at these three and the bottom five, these peak profiles are quite different, indicating that these two structures are completely different phase. And this peak position can be mixed by the two-dimensional hexagonal lattice, indicating that this material is hexagonal columnar structure. And above the 1.55, we have a cubic. This is the cubic phase structure. And at the W is equal to 1.55, we have a bimorphic behavior of the hexagonal phase and the spherical phase together. So this data summarizes the change of the intermicellar distance. The initial decrease is due to the close packing, due to the increased population of the micelle. So based on this sense data, we can summarize this kind of structural model. As you can see, the water content is less than, W is less than the 1.58. We have a columnar phase. when you increase a little bit more, this volume ratio is changing. Then the morphology is changing abruptly to show this kind of micellar structure. So when you change the water content in the Joseph's solution, we can change the morphology of the nanoporous polymer material very easily. So what we can summarize from this research is following, and then in order to change the morphology of the nanoporous silica material or nanoporous polymer material, we can simply change the molar ratio or mass ratio between the inorganic compound and the ethylene oxide unit, or the water content and the ethylene oxide unit in the black polymer. Okay, that's it. Thank you for listening. Okay.